Last one, number 5 here. This is the same thing as number 4, except we're just going to go in reverse order. In number 4, I gave you the wavelength and wanted you to get the energy. In number 5, I'm giving you the energy and I want you to get the wavelength. Now, please note that this one starts off by 203 kilojoules per mole of photon. So remember that the first thing that you have to do is you have to get this into joules, because all of our equations up here that we have are in joules. But also remember that it only works for one photon, and right now I have given this to you that it is a mole of photons. So we're going to have to do 2 quick transformations at the start of this problem to get these numbers to the point that we can do something useful with them. The first is we're going to have to convert this kilojoules into joules. So that's easy. 203 kilojoules times 1,000 joules per kilojoule. That's going to get us 203,000 joules. Except remember, that's per mole of photons. Right? That is per mole of photons. We don't want a mole, we want a single photon. So we've got to divide that by Avogadro's number. So this is 1 mole divided by 6.022 times 10 to the 23rd photons. And once you end up doing the math on that, you end up with an energy factor of about 3.37 times 10 to the negative 19th, and that is in joules per photon. Okay, now that's your energy for a single photon, but I don't want the energy, I want the wavelength. Okay, fine. We can just use our equations and go to town. It's the same ones we've been using all along. E is equal to h times the frequency, so 3.37 times 10 to the negative 19th joules per photon is going to be equal to 6.626 times 10 to the negative 34th times the frequency. And so the frequency then turns out to be in the neighborhood of 5.09 times 10 to the 14th inverse seconds for that photon. Then what we're going to do is we're going to turn that into wavelength. So that is now our original equation. C is equal to the wavelength times the frequency. So 2.998 times 10 to the 8th, and that's in meters per second. That's going to be equal to the wavelength, which is what we're looking for, times your 5.09 times 10 to the 14th inverse seconds. Because again, that's our frequency. And the wavelength then turns out to be 5.89 times 10 to the negative 7th, and that's in meters. But remember, we don't want it in meters, we want it in nanometers. So consequently, then our last step is to take our 589 times 10 to the negative 7th nanometers and multiply it by 10 to the 9th. Oh, I'm sorry, that's in meters. My bad. Times 10 to the 9th nanometers per meter. There we go. And so you should end up with 589 nanometers. So 589 nanometers, if you check a visible spectrum chart, and no, you don't have to have that memorized, but if you check that 589, 509, just below 600, so 600 here, a little bit below that is definitely in the yellow.